you a few factors about yesterday's lecture, correction and notation. The TB plane, we considered two states, state 1 and state 2. State 1 is characterized by T1, T1, this by T2, T2. Focus on part A. So change in notation that I want is, I regarded the volume corresponding to this state. This state actually corresponds to T1, T2. So since I remember calling the state itself as A, I would have you replace the V2 by VA rather than V2 because if I want to use the volume for this, it should be V1. This is a change in notation. Because actually the volume that we wrote as V2 should actually be the volume corresponding to this state, which I wanted to change the notation as VA because it's more appropriate to call this as V2. We would encounter that volume when we integrate along part B. So what is important to understand, and you might have realized that even though the specification might be in terms of T and B, right, and we would automatically, for this segment, we would write the change as integral P1 to P2, dH by, let's say dH, let's take U to be. This form is not practically very useful, and we are forced to convert it to the dB domain. So you might argue that why not work in the dB domain directly? That is certainly possible, but invariably you have to find the volumes V1, V2, or whatever other volumes are required. So the specification is in terms of P1 and P1. Whatever domain you work in, you have to find the volumes from the equation of state. Right? That we will probably address later. So, actually what is practically needed is P1 to VA dH by dP expressed as a function of V rather than P, and then we convert this whole thing into an integral over P, so obviously we will get dP by dP again. This is what we have, and for dH by dP, so then this becomes integral V1 to V2, or rather VA, sorry, V1 to VA, and this would be, this would be plus P, so I can write this simply as V plus P1 dP by dP divided by dP by dP of P1. The whole thing now as an integral over P. And so I could do the, I use this slightly different version of the, so there's no need to separate the way we handle these two integrals. This can be also written, the first term I wrote yesterday as P in terms of dP as it is originally present. I just substitute here V plus something dP. So I have dP that I wrote as PV between the two states, right? And it's not 1 and 2 actually, it's rather between 1 and A, right? Minus integral P dP. That formula can also be, a different version of the integration by parts can be also used. I have E1 to dA, V dP by dP of dP1 dP. I can use this formula A to V f of x d prime of x dx is fg between the two limits, right, A and B, minus integral g of x f prime of x dx. So here, which is in this version of the integration by parts, clearly f is v. And what is g? What is the function g? It's p, right? P of v evaluated at t1, right? So this would again be p times p between the two limits 1 and a, right? Minus integral. So g of x is simply p, right? F prime of x, it is dv by dv, which is 1. So this will simply become this, and we recover the same formula as we had. So whichever version of the integration by parts you use, I would say this is better, because we once and for all convert this to an integral over v and then implement whatever we have. The way I did it last time, it appeared like we have to handle that one separately in the p domain as an integral over p, and then handle this separately. That's not really required. So I make a transformation once and for all. That's what you have to remember. So not only do we have to convert the integrand in terms of v and d, but also the integral itself. So that would require this additional term dv by dv in place. So that is what is generally. So if we want to work in the dv domain, right, then I can do that, and we do that through the departure functions. I can also work in the dv domain. So I mark all these states in the dv domain, right? And so I would there choose a constant volume part and a constant temperature part. So those integrals would look a bit different, right? And there we are approaching v directly, so there's no question of va. We could be either v1 or v2. You can try that, but we'll do a version of that when we look at the departure function. So now we move to look at departure functions. Either departure function corresponding to a specification T1 and P1, or a departure function corresponding to a specification T1, the temperature and volume of a particular state. The state is the same. So when I talk about state 1, it has temperature T1, pressure P1 and volume V1. I need only two variables to specify the state. I can either choose the temperature and volume, or the temperature and pressure, or the pressure and volume, which is not normally done. Right? So common specification would be obviously temperature and pressure. But we will see the departure function in the dv domain is actually easier to do, because we don't need all this transformation of integral. It's automatically. So even if I were to look at this, right, I would still have to convert it to the v domain, because I am given the pressure in terms of T and V. So if I want to use that, and all of the derivatives are expressed in that way, in terms of pressure explicit quantities, in the pressure itself or the derivatives of pressure with respect to temperature and volume, or just the volume, right? So all our objective has been so far done. So you could see that in fact it's easier to work in the dv domain. But however, in some cases the departure functions would not be the same, depending on the specification, whether it's between T1 and V1 or T1 and V1, it would differ. So you have to be careful then to correct. When starting with this, then to get this, I would have to correct and get T1, V1, VC. Why do they would be different, right? Because it appears that they are corresponding to the same state. Why would it be different? So let me just first write the general formula for any property. So the way we do it is, now the ideal gas is coming. We have to be very careful how we do it. So let me just start from the TP case. Now I am given only one state, right? So that I would mark here as P1, V1. That's the state at which I want the property. But it is not just the property, but it's a difference with the ideal gas. So what I do is, this is the actual substance. This is a very general way to obtain the departure function. And you see the formula is very intuitively clear. Now what I do is I this is the temperature T1. Now, I consider the difference between these two states. One is at T1 P1 and another is at T1 P0. Then I will take the limit as P0 goes to 0. This is the low pressure, right? To the left of this state. Whatever state I am given, I choose a state to the left and take the limit as P0 goes to 0. So now, what is U of T1 P1 minus U of T1 P0? Temperature is the same. How would you write it as an integral? Abhijit, how would you write it as an integral? There are so many integrals like this. Temperature is the same. The general formula is integral du by dt dt plus du by dp dp. So temperature is the same. Only the pressure is varying, right? So how would this integral look like? Integral, first write the integral sign. Integral from what to what? P0 to, good, P0 to P1. So what is the derivative that would appear? By dP at fixed temperature. So, right. dP, yes, that's correct. But I would like to bit more clarity as integral P0 to P1. This is just like, if I have a single variable, I can write f of b minus f of a as integral a to b f prime of x dx. Certainly all of you would immediately write this. Right? If I for instance get you integral a to b df by dx, the integral of that is clearly, right, you would simply cancel. You have a way to move it. You would simply get this, and a to b df is written as f of b minus f of a. The derivative of the integral between two limits, the integral of the derivative, right, between two limits is simply the difference between the function whose derivative is there in the integral. This is just a generalization. Of course, if both pressure and temperature are varying, you would have an integral over both P and T. But here, for the departure function, it's always an integral only over P or V, whichever variable you consider. Right? So that is why the departure function would depend only on the equation of state. We will see all this. So I would write this as du by dP as a function of pressure evaluated at T1, this integral. Now I consider the ideal gas associated with that substance. This is an important concept that for every substance, no matter what the temperature and pressure, right, you can talk of the ideal gas corresponding to that substance. Right? So the ideal gas corresponding to the actual substance, I will consider it from the same state, T1, P1. It's only a hypothetical. It doesn't mean that at the given temperature T1 and P1, the substance is going to behave like an ideal gas. But I can hypothetically consider the fictitious ideal gas corresponding to that substance, and I can consider its property at any temperature and pressure, even though the actual substance may not behave like an ideal gas, right? So this is the ideal gas between the same two states, P1, P1 and P2. So what would this be now? U ideal gas, P1, P1 minus U ideal gas, P1, P0 is integral P0 to P1. Same integral, but now this is the property associated with the ideal gas of that substance. Now I'm going to subtract the two because I need this. Right? So we subtract the two, what would happen? U of P1, P1 minus 2Ig of T1 T1. This will be one term, right? Minus 2 of T1 V0 minus 2Ig of T1 V0 can be written. Now both of these are integrals from P0 to P1. So to combine them into one integral P0 to P1 du by dp Are there any questions about what we have written so far? So I consider the substance at the given. So what is specified is T1 and T1. So I consider another state at T1 at a pressure lower than T1 that I can always consider. Right? Same two states. So one is the actual state given, other is I am creating that. For a reason that will become clear. Right? So look at the ideal gas associated with that substance and consider the property change of that fictitious substance, right, between the same two states. One the actual state of the substance and another the state that I create. Now what I will do is I take the limit as P0 goes to 0. So what will happen to this difference as P0 goes to 0? It will become 0. There I make use of the property that at a given temperature, any substance in the limit V going to 0, P0 going to 0, will behave like its own ideal gas. That is what it means. Right? Physical idea, the experimentally observed idea that at sufficiently low pressures, every substance will start behaving like its own ideal gas. Right? So that I use to cancel this difference in the limit as P0, not at other pressure. In the limit as P0 goes to 0, this will become, and so this will now become 0. So I can now write the formula. I think is very simple and easy to write. U minus, so the departure function of any property defined like this, the specification of temperature and pressure, is simply integral 0 to P1 of the integral. It is the integral of the departure function of the derivatives. So it is very easy to write down and remember. Right? The departure function at a fixed temperature and pressure is simply the integral from 0 to P1 of the departure of the derivatives with respect to pressure. When you integrate the derivative, you get the function, something like that. Right? So it's easy to write this without any further proof. So this gives us the formula. Now I know that this formula by itself will not be directly useful because again I have to express it in terms of volume anyway. But the formula is this, right? So if I want to use it, right, then I will have to write this du by dt, but now has to be expressed in terms of the volume. This doesn't change, this doesn't become V. It remains as P, but I have to express, I am now making the transformation for this integral. P as a function of P and T1, right? So this would be V1, where V1 is V of V1, P1. That's the volume of the actual state. So when I am given P1 and T1, I have to also know effectively what its volume is. I may not specify it, but then I have to go and find it from the equation of state, right? So now, what would be the lower limit? Infinity, right? It would be infinity because we make use the idea that if P equal to RT by P, this is the ideal gas equation, so a fixed temperature. So P goes to zero limit corresponds to V going to infinity. If you can accept that, that means that at a fixed temperature, as you take the substance to larger and larger specific volumes, then it will approach the ideal gas state, right? So that is the idea that we would use, and if you can accept that idea, then it becomes very easy to write the departure function for the temperature volume domain. So I will write it. So all I have to do there is for the actual substance, this is P and P. So I am given this. I am given T1 and T1. So I have to consider a very high, let's say P naught, right? And then take the limit as P naught goes to infinity. Do that for the actual substance, do that for the ideal gas and subtract. And again make use of the idea that at sufficiently large specific volume, the substance will be at a given temperature. That's very important. Substance will behave like its own ideal gas, and then you can easily verify that I'm not going to prove it all over again, but you can easily prove this following ideas very similar to what I used to prove it in the temperature pressure domain. I'll get that. So the departure function in terms of the specification of T1 and T1 is again the integral of the departure of the derivatives now with respect to volume. Right? The derivative of the actual property of the actual substance minus the derivative of the property associated with the ideal gas, but now expressed as V and T and integrated over volume. The limit is from infinity to the volume of the actual state. Are there any questions on the general formula? Now we'll apply the general formula to particular properties and see how it works out. Any questions on this? If you know, basically main point is given two states, whether it is the actual substance, whether the temperature, pressure, volume, what is specified, what is changing, you should be able to write it as an integral. That's the basic idea here, right? We've seen different possibilities. If you come to departure function, the only variation is either with respect to pressure or with respect to volume. Temperature doesn't change. That is why the specific heat data doesn't come directly into the picture when evaluating the departure function. It can be evaluated based on the equation of state alone, right? So with those ideas in mind, we will now take up a specific example of U equal to H, let's say. Now I want to calculate H minus HIG, T1, T1. Right? So again I will write dH by dP is what I want. Right? So first let me write down the formula. So now this will be again infinity to V1 because I have to deal with the volume integral. Even if T1 and P1 are specified, I have to deal with it in the form of a volume integral, right? So I have dH by dP dP1. So now what is dH by dP? We've already seen that right? dH by dP was, if I remember right, d plus d dP by dt divided by, I have to write it properly. I'll write it in terms of T1, right? So now this will automatically be a function of V and T. Yes. Now, what is dHIG by dt? It's 0, right? So because ideal gas doesn't depend on the pressure, depends only on the temperature. So for the H and E, this term in the departure function formula would vanish, right? So all I have is H minus. We've already actually got it sort of indirectly, but I'm going to do it more systematically. Integral infinity to V1. So I have to write only this, right? So this would be V. V itself, now I don't have to write the temperature and pressure. V is the variable, right? Whereas T1, this is important. We've already encountered this integral, so it should not be that difficult. I'll write it properly because the limits are different. Here it is infinity to V. There we consider earlier V1 to VA, but all that doesn't come in now. Between the limits, right, E going to infinity and E going to V1. Between those states actually, because here you have the pressure also, right? So now, plus integral infinity to V1, right? V1 can be taken outside, dP by dt. That's all. I cannot do anything more because I am not yet given an equation of state. You have to leave it like that. All I have to make sure is given an equation of state, can I evaluate these quantities? Right now, what about this? So at the point, this corresponds to the actual state of the substance. There's only one state of the substance, and then the ideal gas state at the same temperature. So V going to V1 would be V1 times P evaluated at V1 T1, so that would simply be V1 T1 minus the lower limit. What is the plot? So you have to be very careful. Otherwise, you are getting an infinity, and you just wonder what the infinity times and what is P is. So you have to understand the V going to infinity corresponds to the ideal gas state. For the ideal gas, PV is simply RT. Right? But it's the ideal gas state at the same temperature. So I have to write this as RT1 because it's the product PV as the substance goes to the ideal gas state. Now the product goes to RT1 here because that is the temperature of the ideal gas that I am considering. Yes? T1 P1. T1, this is T1 P1. That is when we get the integral over with the derivative with respect to P, but it is expressed as a function of V and T. T1 dP by dt, this will cancel. Yeah, numerator is T1 dP by dt evaluated as T1. It's not constant. It's a forget about t1 and all. D is a function of b and t. So what is dp by dt a function of? Also of b and t. Right? If I have a function f of xy, if I differentiate it with respect to x, let's say, I am going to get another function of x and y in general. Sometimes, for example, if I have x times some g of y, then the derivative with respect to x will just be a function of y. But in general, I have f of xy. If I differentiate it with respect to x, I am going to get another function of x and y. Right? Now, so this is also a function of p and t. Now I can evaluate this function given the values of volume and temperature. But here I am considering the derivative as a function of p evaluated at t1. That is what this quantity represents. Right? So it is not a constant. P means keeping b constant, I take the derivative. That is still a function of b and t. It's not a constant with respect to b. You have to understand the whole notion of what is meant by a function and its derivatives. This is a notation that I am using to make it very clear that it is actually a function of b and t, but I am evaluating at t1, otherwise this integral doesn't have any sense. If I just leave it like this, arbitrarily, without the semicolon, it has no meaning because what is the temperature? It can be actually a path integral where the temperature also changes with volume. But however, I am considering this integral at a fixed temperature. So dp by dt, which is a function of volume and temperature, when evaluated at a specified temperature T1, becomes a function of volume alone. That I can integrate over volume between the limits infinity and a particular value v1. Right? That is the meaning of that derivative. So I don't see any contradiction. Right? So that's what I have written. Right? So it's a function. The function of volume is here dp by dt. It's a function of both volume and temperature in general. Right? So for the van der Waals, for the ideal gas dp by dt is independent of temperature. So R by P. In fact, even for the van der Waals equation of state, RT by P minus P minus A by T squared again will be independent of temperature. That is very specific case, but in general, it will depend on temperature. So I have to make sure I write that for the state. I am not taking particular equations of state here. Right? So that is the meaning of that. So this is the final formula for the departure function of H when temperature and pressure are specified. Now let's look at what happens when the temperature and volume are specified. So, right? So H minus, you see why they need not necessarily be the same always. Let's now write on the face of it, doesn't look like they are going to be the same. Let's see what happens. Integral infinity to d1. Now I will have dh by dp. This is not the same as this, even though they both express the derivatives in terms of b and t1. One is a derivative with respect to p, another is a derivative with respect to p. They will obviously not be the same, as in fact you can verify from the formula. Now, one thing I can though say is that this is again going to be 0. So, what is dh by dp? Can you look at the notes and I hope you, at least some of you have written these formula. I clearly remember deriving them. What is dh by dv? Does anyone have that formula? H as a function of b and d. I very distinctly remember deriving this. Yeah, can you come and write on the board? Somebody else maybe. Can you come and write on the board? You have that formula? dh by dv. I want in terms of pressure explicit. It will automatically come in terms of pressure explicit. Yes, yes, maybe you have it or not. You don't have it. It's a convenient way to avoid coming to the board. Good. So I have this. So now it's evaluated at T1 and V1. So the integral is, I have to be very careful to write the T part of it. Integral infinity to V1. T1 dP by dt, again, to the function of volume, but evaluated at T1. And then plus V dP by dt. So here there is no need for transforming the integral. It will automatically be in the volume. So clearly you can see h minus Hig. The dV, or for that matter any property, would be easy to handle in the volume domain. Right? So now, are these two the same? Probably you can easily prove that they are the same. Right? Because this is going to be dP by dt. It's actually very easily seen from here. They will actually be same. Right? They are actually the same. Because we get the same term. So I can write this as integral infinity to V1 V1 dP by dt dV. Yeah, here. Yeah, below. No, there's no, this is what is already here. There's no further transformation required. That's what I'm saying. I'm not able to see what your objection is, but anyway, then I have plus integral infinity to V1 V dP by dt. And this will again, by integration by parts, we get V times P evaluated between the infinity, that the ideal cascade is the actual state, minus integral. Oh, we need to get another. Oh, I'm sorry, I missed out another term here. That's why. Because I know the answer that they have to match. V dP by dP. I forgot to write the other integral. Fg I have written. Right? It is Fg prime of x. That would be Fg minus integral G F prime of x. So that term would be minus integral, right? V dP by dV. So this is Fg prime. The Fg I have taken care of, minus G, which is P. F prime is 1. So it will be derivative with, so that would be another term, minus P of dP1 dV. That's what I would get here also. So it's important actually to combine these two integrals over V. This is also an integral over V. Right? So let me write it properly. You can easily show that both of them will be plus, I combine the two, minus, so this will come in the integral. So this is the final formula for the departure function. Whether you get T1 and P1 are specified or T1 and P1 are specified, the answer will be the same. So effectively you get and that is equal to this integral. It is important to combine these integrals because you will find that actually blow up, because if you integrate from V to infinity of the pressure, might blow up. So, but anyway, but I think if you combine it, it probably would not cause any problem. But that's the final answer. So let's quickly do the same thing for S. Right? So let's take U equal to S. So now I calculate S minus SIT of P1, P1. Now this is important because ds by dp is, we know from one of the Maxwell's relation, dp by dt, it is actually, there will be a negative coming from here. This would be dp by dt, dp by dp. So let's write first the integral. Integral infinity to p1 ds by dp, evaluated as express the function b and d1 minus ds ig. This will be the first important change. In that, ds ig by dp is not zero. The entropy of the ideal gas is not independent, it depends on both pressure and temperature. What is dsIT by dP? You have the formula, very easily calculated from this, minus dP by dt. What is that? So the ideal gas. Minus R by P, right? So what I will get here is, and I want that to express in terms of V, right? So R by P is equal to RT1 by P here, evaluated at P1. So R by P is also equal to minus P by P1. Right? Because I want, anyway expresses the integral over V, so let me stick to that and not evaluate that. Probably can be evaluated separately, but I don't want to do that. Right? So this will be integral infinity to V1. Let's write it down. First dP by dt minus, right, R by P, which is actually plus V by T1, right? Does it make sense or not? So now again, I have dP by dt, which is integral infinity to V1. This will cancel the first term, the dP by dt will cancel. So again I have dP by dt dV. What about the other term? That would be 1 over T1. Right? 1 over T1. This is actually also I should have as D. That's why it's very important not to miss out or, be lazy and not write out the thing. Otherwise you just have D over T and you won't know what to do with that T. So this is all at T1. So again, I have integral infinity to V1, V dP by dt. There is no sort of how to integrate. Right? This is what it is. And so, this would be integral infinity to V1, dP by dt. I don't know if I missed out any terms, but plus 1 over T1 times, so dP minus integral P dV. So that would be again T1 V1 minus R T1, right? And then minus integral P of the 1 over T1 will have dV right? It's not surprising, I mean, because the entropy always has a per Kelvin, per temperature. That's why, whatever you're getting here is being divided by T1, right? So that's what I have. So I can combine this and it can be infinity to T1 dV by dt minus 1 over T1 P. We run out of time, so we have to dV, and then again I have plus 1 over T1 d1 by T1 minus R is what I seem to have, right? So I'll just leave it at this. Might not be the most convenient form. So what I want you to do as an exercise before you come to this class is calculate S minus SIG as T1 V1. So I want all of you to do this because it's the only way you will learn how to handle these departments. It's actually easier to do. All I need is ds by dv and SIG by dv. Express the function of v and t, t1, right? And I want you to check whether this is equal to S minus SIG at T1, P1 or not. So you have to know how to first do that independently, then try to combine the two, compare the two, and see if they are equal or not. Are there any questions? Quick questions.
How do you get that 1 by T1, T1?
Yeah, that is because it's coming from V by T1, dV by dV. 1 by T1 can be taken out, and I have dV by dV. Anyway, you take a look at it tomorrow because we run out of time. I don't want to